Alright, this video is a continuation of Module 9 on stoichiometry. I'm going to go through a hypothetical example here involving the reaction of sodium bicarbonate, which is just baking soda, with acetic acid to produce water, sodium acetate, and carbon dioxide. So this is just the famous volcano experiment you may have done at home, where you mix baking soda with vinegar and it makes lots of bubbles. That's exactly what's going on here. Now, something you want to point out about this reaction: the coefficients in this case are all ones. So it's not written, but it's implied that we have 1 mole of sodium acetate reacting with 1 mole of acetic acid that makes 1 mole of water, 1 mole of sodium acetate, and 1 mole of carbon dioxide gas. Now the vinegar is made up as 5% acetic acid and water. So if you go to the store and buy standard vinegar, it's most likely going to be 5%, which means 5 grams of acid per 100 milliliters of water solution. Now in this particular example, let's say I use 25 milliliters of vinegar. So if I take 5 over 100, which is the 5%, multiply that by 25, that'll make milliliters cancel. And now I convert moles, I convert the number of grams of grams of acetic acid into moles. The molecular weight of acetic acid is 60.06. That makes the grams cancel out, giving us 0.02 moles of vinegar. 0.02 moles of acetic acid. When you hear the term vinegar, that means acetic acid in water. So you have to be a little careful about the terminology here. You have 0.02 moles of the acetic acid. The rest of it's water, it's just pure water, by the way. Now the baking soda, that's sodium acetate. That's sodium bicarbonate. And this we can weigh out as a powder. So let's say you have 3.5 grams, a molecular weight of 84.01, that's 0.04 moles. 1.8 grams is 0.02 moles, and 0.9 is 0.01 moles. Notice here I have, this is going to be 2 times the number of moles of acetic acid. This is equal to the acid, and this is just 1/2 the acid. Alright, so that summarizes all this here. Now, what we did, if you take the baking soda, we're going to put that into balloons. So the one with the most baking soda, I'm going to call that red. The one with the middle, I'm going to call that yellow. And the one at the bottom is going to be called the least, will be called green. So again, this table, here's the balanced equation. We have 0.04 moles of baking soda, 0.02 moles of acetic acid in all cases. The question now is, how much carbon dioxide are we going to make? And how is that going to affect the size of the balloons? Remembering that the coefficients are all 1 to 1 to 1. 1 here, 1 here, and 1 here. So how much CO2 should we make? The balanced equation says that for each of these should run out at the same time. So as you use 1 molecule of baking soda, we're going to use 1 molecule of acetic acid to produce 1 molecule of CO2. If I use 10 molecules of baking soda, that requires 10 moles of acetic acid to make 10 moles of CO2. This is because the equation is 1 to 1 in all cases. So as I use, these are going to get used up at the same rate. That's the point. I'm going to use this will be all used up at the same time. So what does that imply about the number of moles of CO2 I can make, for example, from the yellow one? For every acetic acid I use up 1 of the sodium bicarbonate. That implies you should make 0.02 moles of CO2, which will inflate the balloon a certain amount. Now what about the green one? What happens when I use up 0.01 moles of baking soda? If I use up all of this, how many moles of acetic acid am I going to use? Do I use up all of it? No, I'm only going to use 0.01 because I can only use as much as I have baking soda. So when this reaction is over, I should have some extra acid left. Namely, I should have 0.01 moles of acid remaining. Now what about the CO2? This gets produced at the same time I use up the reactants. So product is being made at the same time. So therefore I should only make 0.01 moles because I did not use up it. I didn't have enough baking soda to use up all of it. Sorry, I didn't have enough baking soda to use up all of the acetic acid. Well, if I only have 0.01 moles of CO2, compare that to 0.02 moles of CO2, which balloon should be larger? I expect the one with the more CO2 to inflate the balloon the larger size. Now what about the red balloon? In this case, you've got 0.04 moles of baking soda, 0.02 moles of acetic acid. What runs out first this time? What should happen is that I will use up all of the acid. You subtract these, I should have left over baking soda. You should have 0.02 moles of baking soda remaining. Now what about the CO2? If you use up all 0.02 moles of acid, I only use up 0.02 moles of baking soda, you should only make 0.02 moles of CO2. So what does this all tell us about the size of the balloons? We should be able to agree that the green balloon should be the smallest, because that makes the least amount of gas. What about the red and yellow? Is red going to be larger than yellow? Or are they going to be the same size? And that's actually what happens. Turns out the red and yellow balloons end up being exactly the same size just because of the amount of CO2 we produced. And this shows exactly the same thing. So the amount of CO2 gas produced was limited by the amount of baking soda in the green balloon. In the case of the red balloon, there was not enough acetic acid to react with the excess baking soda, and the yellow reaction had the proper amounts of each. So in yellow, we actually have what we know as a stoichiometric amount of each reactant, because they both ran out at the same time, leaving 0 moles left over. But you can see from this example is that this number of moles that we have is what matters the most, not the number of grams. But we're always going to go from grams to find number of moles of each, and then to figure out how that's going to relate to one of the products. And you're going to do a lab with this. If you're in a lab class, we're going to do a lab experiment very similar to this, where it's going to be sodium carbonate, Na2CO3 instead of sodium bicarbonate. That's going to change the coefficients. That will change the coefficients of the reaction. But we're going to do a very similar experiment on the same idea.